Hello class 12 students, stop scrolling right now. If solution chapter is still confusing you, this quick revision series can literally save your board marks. This chapter carries direct numericals, direct formulas and very predictable questions in CBSE. No long explanation today, only exam focused revisions from your syllabus. So keep your pen ready because whatever appears on the screen now can appear in your board paper also. So as you know that this chapter is the solution. So what is the solution? Solutions are nothing, just these are the homogeneous mixtures of two or more than two components, and these components may be solid, may be liquid, or in the gaseous states also. So in the case of the binary solutions, there are the two constituents for these solutions. One is the solute and second will be the solvent. Solute, right? Solute is the substance that is dissolved in another substance in a lesser amount. Like you can take the examples like can be the sugar, can be the salt, can be the anything. Anything means can be in the forms of the solid state. You can consider them as the solute. Similarly, solvent is the substance in which the another substance is dissolved in a large amount, forming a solution. Examples you can take like water, milk, means any other things that is generally found in the case of the liquid state. You can consider them as the solvent. Examples you can take water and milk. So now I'm giving you a concept that will boost your knowledge. So we can say the solvent determines the physical state in which the solution exists. Now the topic is we will learn about how we can express the concentrations of solution. But before that, first you should know about the concentration. What is the concentration? Concentration is nothing, just it is the amount of solute present in the given quantity of solute or can be in the forms of solvent. Concentration of solution can be expressed in any of the following ways. We can define as the mass of solute in the solution divided by total mass of solutions times 100. The thing is, concentration described by mass percentage is commonly used in the industrial chemical industries. Similarly, we can express the concentration of solutions in the terms of volume also. So we can define as the volume percentage as the mass of solute divided by the volume of solution times 100. So it will give us the volume percentage. One more thing, volume percentage is represented by a small v divided by capital V. And the thing is, we use the concept of the volume percentage, like 35% of the volume percentage of ethylene glycol is used as the antifreeze in car just for the cooling the engine. There is one more applications of the volume percentage, like it is commonly used in the medicines and the pharmacy as well. Now, sometimes we express the concentration of solutions in the terms of ppm. ppm means basically the parts per million. So we can define as the ppm as nothing, just the number of parts of the component divided by the total number of parts of all the components of the solutions times 10 to the power 6. We use the ppm concentrations of the pollutants in water or in the atmosphere that is often expressed in the terms of ppm. Next topic is the mole fraction. Mole fraction is generally represented by the capital X. It is also a ratio, so we can define as the mole fractions of a component as the number of moles of the component divided by the total number of moles of all the components. I am giving you the concept about the mole fraction. Mole fraction is the independent of the temperature. Is the molarity. Molarity is represented by the capital M. It is also a ratio of the number of moles of the solute divided by the volume of solutions. Make sure in liter. Volume of solutions should be in the liter. But before this, we have to find out the number of moles. So for finding out the number of moles, we will use the formula like mass divided by the molar mass. Basically, molarity varies with the temperature because volume depends on the temperature. Means in a simple way, if the temperature will increase, the volume of substance will also be increased. Next is the molality, that is represented by the small m. So basically it is also a kind of ratio, that is the another formula. So we can define as the molality as it is the ratio of the number of moles of the solute divided by the mass of the solvent, but in the kg. So molality is also the independent of the temperature. Why? Because mass does not depend on the temperature. Now the solubility. Solubility is nothing, just the maximum amount of solute that can be dissolved in 100 gram of solvent to form the saturated solutions at a given temperature. that is known as the solubility of the substance. Now one more thing that is important here, a solute dissolves in a solvent only if the interactions are similar in the both of them. Next is the saturated solution. It is a special type of solutions, one in which the no more solute can be dissolved at the same temperature and the pressure, and just opposite the unsaturated solutions. It is a type of solutions which more solute can be dissolved at the same temperature. Now, what are the factors where the solubility of solids in liquids depends? So we can say the solubility of solids in which liquids increases with the rise in temperature, and if the dissolutions process is endothermic. One more thing, the solubility decreases if it is the exothermic. However, there is no effect of pressure on solubility of solids in liquid. Now, what are the factors where the solubility of gases in liquids depends? Like we can say the solubility of gases in liquids increases with the increase of pressure and increase with the decrease of temperature. Law of Henry is very important in the terms of your exams. Law of Henry, actually, according to this, at certain temperature for a given volume of the solvent, amount of gas dissolved is directly proportional to the partial pressure of the gas. It can be stated as the partial pressure of the gas in the vapor phase. Let's suppose this is the P here, that is the proportional to the mole fractions, that is represented by the X here, will be directly proportional to the mole fractions. One more thing, here this KH is the Henry Law's constant. I'm giving you the application that is based upon the Henry. Actually, you know, the aquatic species are more comfortable in cold water rather than in warm waters due to the presence of more dissolved oxygens in it. Vapor pressure, as the name suggests, like the pressure exerted by the vapor over the liquids phases at the equilibrium state at the constant temperature, is called the vapor pressure. Vapor pressure actually nothing, it depends on the nature of the liquid and the temperature. Means we can say that the vapor pressure increases with the increase in temperature and the vice versa. Raoult's law is very important because in the exams multiple questions can be asked from here. So for a solutions of the volatile liquids, the partial vapor pressure of each component in the solution is basically the directly proportional to its the mole fractions. Let's say in mathematically we have the two liquids, like for the components of A we have the pressure at point A. So according to the Raoult's law, it will be equivalent to the pressure P naught of pressure at point A will be times the molar fractions at point A. Similarly, we will find out the pressure at point B. So the total pressure will be equivalent to the sum of these pressure at component for A and B. But what will happen, like the solutions containing the non-volatile? So in this case, for the non-volatile, Raoult's law states that the relative lowering of the vapor pressure for a solution is equal to the mole fractions of the solute. So in mathematically, we can say that the P naught minus PS divided by P naught is equal to the small m divided by small n plus capital N. One more thing, P naught is basically the vapor pressure of the pure solvent and PS is the vapor pressure of the solution. Small n is moles of solute and the capital N is moles of solvent here. Colligative property, this is the most important topic because in the exams many questions asked from this topic. So it is nothing like there are some certain properties of solutions that depends only on the number of particles of the solute and do not depend on the nature of solute. So such particles are called the such properties include the relative lowering of the vapor pressure, depressions in freezing point, elevations of boiling point, and the osmotic pressure of the solutions as well. So the question is how we can calculate the molality from the relative lowering of the vapor pressure of the solutions. Of course, we will use the formula that is P naught minus PS divided by P naught times 1000 by capital M. Capital M is basically the molar mass of the solvent here. Now we have the another formula for finding out the calculations of the molality from the elevations in boiling point of the solutions. We will use the formula here, like the molality of the solutions will be equal to change in TB divided by KB. Here this del TB is nothing just the elevations in the boiling point and the KB is nothing just the molar elevation constant of the solutions. One more thing, here we will take the value of K is equal to 10 times KB and KB is nothing just the molar elevations constant. So when we will substitute these values in equations 1, we will get the value of change in TB is equal to Kb times molality, and after substituting all these value, we will get the Kb times W, that is a small w here, times 1000 divided by capital M times capital W. Again, here small m and capital W are the weight, means the masses of the solute and the solvent respectively, and the capital M is basically the molar mass, that is also known as the molecular weight of the solute. How we can establish the relation between the elevations in the boiling point and relative lowering in the vapor pressure by using a mathematical formula, that is nothing, just change in the boiling point will be equal to the 1000 times Kb divided by small m times change in P divided by the P naught. Of molality from the depressions in the freezing point of solutions, we will use like the basic formula, like the molality of solutions is nothing, just change in TF divided by KF. Here change in TF is the depressions in the freezing point and KF is the molar depression constant of the solutions. Again, we will take the constant terms here, that is K is equal to 10 times KF. So when we will substitute these values in equations 1, we will get the value like change in TF will be equivalent to this term. Now the relationship between the depressions in freezing point and the relative lowering in the vapor pressure will be equivalent, and the relationship between the depression in freezing point and the elevation in boiling point, we will use these relations. One more thing, these relations will be only applicable when the solutions have the same molality. Osmosis pressure, as the name suggests, it is a type of pressure. So actually what happened in the case of osmosis, there is a net flow of the solvent to the solutions in a semi-permeable membrane, and in the case of the osmotic pressure, it is also a type of pressure, but it is the extra pressure applied to the stop to the flow of solvent to the solutions across a semi-permeable membrane. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. It is like how we can establish the relationship between the osmotic pressures and the relative lowering in a vapor pressure. So we will use this formula. One more thing, here capital D is the nothing, just the density of the solution. Small s is the solution constant, change in P, basically the lowering in the vapor pressure. Capital T is the absolute temperature, capital M molar mass of the solvent, P naught is the vapor pressure of the pure solvent, small n is the number of moles, capital V volume of solutions, of course in liter, and capital R is the gas constant. Now we will discuss the very important topics like only the definition portions. So yes, we have the hypertonic solutions. So as the name suggests, it is a type of solutions like its concentration is higher than the that of the solution, separating it by the semi-permeable membrane. Just opposite of the hypertonic, we have the hypotonic solution. So actually in this type of solutions, the concentration is lower than that of the solution, separating it by the semi-permeable membrane. After the hypotonic solutions, we have the isotonic solution. It is a type of two solutions having the same osmotic pressure at a given temperature. As the name suggests, in the next topic like the abnormal molecular mass, so for the substances undergoing the association, dissociations, etc. So in the solutions, molecular mass determined from the colligative property is different, either lower or higher. So from expected value, this is known as the abnormal molecular mass. The most important in the solution chapter, that is the Van Hoff's factor. So basically it is a type of ratio of nothing, just the experimental value of the colligative property to the calculated value of the colligative property. It is also used to find out the extent of the dissociation or the association. You can write the formula for Van Hoff factor as the normal molar mass divided by the abnormal molar mass. Here the thing that we just have to learn, like if the Van Hoff's factor is greater than 1, means solute undergoes the dissociation, and if the value of Van Hoff factor will be less than 1, then the solute undergoes the association. So class 12 students, listen carefully. Chemistry board exam is not about the intelligence, it is about the revisions and the preparations. So if you revise this chapter 2 to 3 times like this, so solutions can become your scoring weapon. If these quick revisions help you, like the video, share with your friends, and subscribe for complete class 12 chemistry quick revision series. Next chapter coming very soon. So revise smart, write smart, score 90 plus. Then see you in the next video. Till then, keep learning and keep smiling.